Welcome to the Water Resources Podcast. I'm your host, Bridget Scanlon, from the Bureau of Economic Geology at the University of Texas at Austin. This podcast is produced in partnership with the National Academy of Engineering. In this podcast, we discuss water challenges with leading experts. I would like to welcome Veena Srinivasan, who is the director of the Bengaluru-based Water, Environment, Land and Livelihoods. That acronym is WELL Labs. That's a really cool acronym, which she started in last April in 2023. And it is a research and innovation center at the Institute for Financial Management and Research. Prior to creating WELL Labs, Veena worked as a senior fellow at Ashoka Trust for Research in Ecology and the Environment, ATRI, where she led the Center for Social and Environmental Innovation. Veena has won numerous awards, the most recent being the 2023 International Water Association's prestigious Water and Development Award for Research. I met Veena almost 2 decades ago when I visited Stanford when she was working on her PhD, and I followed her career and am extremely impressed with her work. So I'm delighted that we will get an opportunity to talk about it today. Her research is transdisciplinary, translating technical knowledge to decision makers and policy makers, and she has a very strong reputation in social hydrology, which I hope we will discuss. So today, I think we will start off talking about her work in South India, in Bangalore, expanding to the entire region, covering rural-urban issues, insights from satellite and ground-based monitoring, and the solutions to the water issues, including quantity and quality, and impacts of climate extremes. So that's a lot of stuff, but we'll try to discuss some of those things. Thank you so much, Veena, for joining me today.
Thank you so much for inviting me, Bridget. It's a real pleasure and an honor to be here.
So Veena, you started WELL Labs last year, and it looks like an extremely impressive center. And I'm just wondering what made you do that? I mean, it's a huge effort and a lot of work, and what were the gaps that you were trying to fill by creating this institute? And maybe describe a little bit about the size of the organization, the types of problems you were addressing. Thank you.
Absolutely. Thanks so much for asking, Bridget. So, as you know, Bridget, I've always been an interdisciplinary researcher. Even 20 years ago, and then through my career in social hydrology, I've always been interested in the linkages between humans and water resources systems. And so I would say that, and I was comfortable through my PhD thesis at Stanford, as well as for the years after, in kind of looking very explicitly at what we call bidirectional feedbacks between how humans influence water resources systems and how water resources and systems influence human societies and decision making. Now, what I realized is that I was doing all of this work. We were publishing papers, we were winning awards for them, and then nothing was changing. And when we kind of dug a little bit deeper into why are things not changing, we realized a few things. One is that one gap was what I call the push and the pull gap. So as a scientist and a scientist interested in having impact on society, I was engaging in what I call push communication. I was saying, here's an interesting paper. I learned this, going to policymakers and saying, here's something interesting for you to know. Most of the time, policymakers just didn't know how to take that information because that's not what they were currently working on, or they didn't have an upcoming question in Parliament coming up, or they didn't have an upcoming policy. And in fact, all of them are so overstretched and so overworked that they can barely keep their head above water, let alone engage with somebody who walks into their office and says, oh, I found this interesting fact about groundwater. So I realized that that was not getting me anywhere. And if I wanted to really engage and move a needle on the ground, I needed to move from push to pull, which means I need to go to decision makers and say, what's a decision you're grappling with today? And what is it that you need information on that I can provide? And then I need to give it to them. Now, if I want to do this, I realized that we needed a very different set of people and a very different set of skill sets that would be able to translate research into impact when you move from a push model, which is really science to science communication, to a pull model, which is really about policy engagement and policy design. And what we realized is, firstly, you need to drop your ego, because as scientists, we are incentivized to push kind of the frontier of the science, right? If you have to do the next new shiny thing, that's what gets you published. Otherwise, you get wrapped by editors who says that, who are going to say this is not novel. But policy makers don't care about whether the science is new or 5 years old. They care that the science is correct and relevant, right? Which means that the most important role your role changes from just communicating science to synthesizing science. And it's not just your science. So think about the kind of work that IPCC does, right? IPCC takes lots and lots and lots of people's science and then synthesizes it for decision makers. And in a sense, we need that kind of mini IPCCs happening all the time, which means that you've got to be willing to synthesize other people's science and not just push the frontier of the science, which is a little bit of a shock at some point when you realize you can't do all of the exciting stuff that you were doing if you're going to do this new role. The second thing that you need to be willing to do is to move from what I call the flip around from looking back to looking forward. What do we mean by that? So most of the time when we're doing science, we understand systems very deeply. But understanding a system very deeply doesn't mean that you know how to solve the problems associated with that system. So there is an element of taking the best state of the science deliberately to design better systems, to design better policies, to design better practice. And that process of taking the best science and flipping it around to actually doing a better design of whether it's about systems of practice or policy is an entirely different skill set. It actually comes from the field of design thinking rather than from the field of traditional science. And so these two pieces I realized were big gaps. And if I wanted to make a difference, I needed to address, I needed to accept that I needed to change into these two things.
I think that's fascinating, Veena. And I commend you. A lot of people come from overseas to go to school in the US and to get graduate degrees and all of that. And to go back to India, then I thought that's fantastic. And I really admire people who do that to try to make a difference in their own country. So it's not just a brain drain, but you're actually giving back then. And then I think it's we oftentimes just go on robotically doing the same things we've always done. And then the metrics for scientists is usually like, how many papers have you published, regardless if anybody is reading them, okay, some people are citing them or whatever. But we need to change that around if we want to be impactful. And I've seen some people, when they ask, they're interviewing people and they ask me for recommendations or letters or whatever, and they say, is their science impactful? Which is a difficult metric. It's not just totting up numbers of papers and something, but it's difficult to quantify. And that's really important. And I think this thing about push-pull, people have so little bandwidth these days. And there's so much information coming at them, they can't make sense out of it. And so what you're doing then, you're trying to make that job easier by figuring out their problems and then trying to develop appropriate solutions that would help them resolve them. So that's a really, and you mentioned the IPCC, Intergovernmental Panel on Climate Change, and you need many types of those to address many of the regional issues that you are working with. So that's really game-changing, I think, and transformative. And so I hope, and as you say, it requires a different tool set and different types of people and more broader thinking. So you're based at the WELL Labs, and I think the acronym is great. Water, Environment, Land and Livelihoods Lab is really, really cool. You're based in Bangalore, which is in South Central India, in Peninsular India. And the geology there and the hydrology is quite similar, somewhat similar, I think, to sub-Saharan Africa, basaltic aquifers, thin aquifers, not a lot of storage in contrast to Northwest India or the Ganges Plain or things like that. So that's a population. Bangalore is a population of about 8 million people, and the metropolitan population may be much larger, about maybe almost double that. And it's considered the Silicon Valley of India, the Garden City of India, and all of these things. So what do you think are the big water issues you are facing there? Because I know you're quite involved with those.
Absolutely. So Bridget, as we're recording this in April 2024, Bangalore is having one of the most serious water crises that it's encountered in recent decades. And I don't know if you remember a few years ago, there was the term day zero that was associated with Cape Town in South Africa. And you might notice that if you read any of the discussion on Bangalore's water crisis, Bangalore is not facing a day zero. It's actually facing a severe water crisis, but not day zero. And I think this is kind of interesting because most people kind of don't understand what's the difference between these things. But I would say what's happened to a city like Bangalore is a very old British cantonment town, and it's at the top of a mountain. The colonial powers, decided that this was a very cool, pleasant climate, a nice place to set up an army cantonment. And so it's at the top of a mountain. The city then, of course, became the center of the high-tech industry, including space, aeronautics, and then later the tech sector, the IT explosion, which happened post-2000 in India. And the population grew very, very, very rapidly. Now, most of the population growth happened in the periphery of the original cantonment town, which is, the city center. The pipe network is all in the city center. Right. So firstly, not only do you have to pump water up 1,000 meters every single day, which is a very carbon carbon intensive and expensive type of activity, but it also doesn't serve the main population growth that has happened, which is the ring around the center of the city, which is where really what we, the part of the city that we really call Bangalore Silicon Valley, which is all of the electronic city, all of the tech parks, all of the massive apartment and commercial complexes that came to service those sectors. And so all of those are actually, or a large portion of those are groundwater dependent. And so the city center actually gets water from the Kaveri. And this year, even though the headlines have been about Bangalore's water crisis, Kaveri water supply hasn't been slashed as much as one would expect. And it's certainly not day zero, which was the complete halt of pipe supply or the anticipated halt of pipe supply in Cape Town. So we're still getting pipe supply in the city center with slight cuts. But it's the periphery of the city, which is completely dependent on these granitic hard rock aquifers, which have very, very little storage. It just can't take the kind of population density that we've designed the city for. And that's the place where groundwater levels have dropped very, very quickly and very, very rapidly. And we've had a massive amount of borewell failures. And that's where you're really seeing apartment complexes running out of water and then having to truck in water, which is very expensive. And then the resident welfare associations are having to grapple with all of the tensions around getting people now to pay for that very expensive water. So it's a very interesting kind of crisis, but I would say it's a groundwater crisis and not a pipe network crisis.
Right, right. So it's interesting to compare with the Cape Town issue, day zero, that got a lot of, news media attention. And there, they were almost 100% dependent on surface water. They had 6 reservoirs that were falling off a cliff, and they had no backup. And that's what resilience means, is to have a number of different sources that you can make the system more resilient. So what you're describing then, Bangalore, almost a kilometer elevation, and then the Kaveri River, which is the main source of water, is down in the valley. So you have to pump it up to the city then. And I like the fact that you also mentioned the energy impacts of doing that. So the cost and greenhouse gas emissions and everything. So pumping the river water up to the high elevation then is pretty energy intensive. And then, you have a rapidly expanding urban area. So this peri-urban area, or the periphery of the main city, then they can't get that pipe network extended fast enough to provide water to those tech companies and stuff. So then they're turning to groundwater. And the groundwater resource is pretty limited. It's weathered basement rock, which is maybe, 30 meters, 100 feet weathered. And then below that, it's fractured. So it's not much storage, not like like the Ganges Basin or things like that. So very little storage. So these are critical issues, and it's very important to understand these issues then in a kind of a holistic view. And that's what I like about your work. You're looking at the whole system: surface water, groundwater, development, urbanization. What do you think, so the city gets a priority over the rural people for water. So if the Coventry River is declining in flow, the city will get priority. And so then the farmers will be, their allocations will be reduced. Maybe you can describe some of this thing, because all over the planet, we're dealing with this rural urban issue.
Absolutely.
And yeah.
Yeah, well, I think that so Bangalore, as you said, gets its water from the Kaveri, and the KRS reservoir it supplies the Canal Command area in surrounding in some of the neighboring districts. And in India, water policy basically dictates that it's a drinking water priority. It's not called an urban water priority. It's called a drinking water priority. But really, there's no way to distinguish. Once you're putting water into a pipe network, you're not distinguishing between commercial, non-drinking water, domestic, and drinking water. So really, in effect, it means that cities get priority over rural areas when it comes to their water supply. Now, if you have a city like Bangalore, where it's maybe in a normal year, only a tenth of the water is actually being allocated to the city, that isn't going to get impacted as the reservoir becomes half, right? Even if it's getting a third of the typical allocation as the city, you're going to have pretty steep declines before the city starts seeing cuts. So most of these droughts kind of get impacted on agriculture. And one of the problems that you see in most Canal Command areas is that they're mostly growing paddy and not very efficiently. And so on one sense, that's a good and a bad thing, because in a sense, if you're using water that inefficiently in a year that you don't get it, you have you have the space to make a cut, right? There's kind of cushion to make a cut. But on the other hand, just as a matter of looking at the productivity of water and what are we doing with water in agriculture, overall productivity of water in agriculture in India is pretty low. And so there's a lot of room for just improving kind of the average use. And I would say within agriculture, making it more efficient and allocating it to crops other than paddy. And then in the urban areas, really thinking about using it more efficiently, but also then thinking about recycling wastewater. So these are sorts of the basket of places where we'd have to look for solutions.
So, I mean, I think a bit of what you're describing then is the legacy of the Canal Command areas that they use to supply water for irrigation. And so you said the main crop then is barley rice. Is that correct?
Paddy,
and
yeah,
so
rice.
is that flood irrigation then that they're doing?
It's still mostly flood irrigated rice.
Right. But what you're describing then is that there's quite a bit of buffer in the surface water supplies. So one of the biggest issues for Bangalore then is that they just can't extend the pipe network fast enough to keep up with the growth and the expansion of the city with the tech companies and all of that sort of thing.
There is a little bit of a twist in the tail. The one part is, can it grow fast enough? But the other twist in the tail is, firstly, Bangalore is reliant on a single source. It doesn't have a diversified portfolio of sources. So that itself is a problem. And the next bunch of sources, Bangalore is kind of at the edge of the Western Ghats. It's a very, very biodiversity rich, a UNESCO heritage site, very high rate of number of percentage of endemic species and so on. And so if Bangalore had to go and get new sources of water, a lot of them would involve drowning or submerging ecologically fragile habitats, which are very, very endemically biodiverse. And so the choice that the city has is, can we use our water a little more sensibly rather than saying that we want to keep kind of, we can get water from the Kaveri and be, not diversified, or we can build new reservoirs in these ecologically fragile habitats. Now, even from the Kaveri is a very, very contentious interstate river basin. And if you've read the news, you would know that over the years, there have been many, many very almost violent state disputes. So although Bangalore has kind of increased its share of the Kaveri after the last set of negotiations, it can't do so indefinitely. Its claim on the Kaveri is capped. And so it would have to go back to the tribunal and renegotiate that. So it does have kind of a cap. It can't kind of grow endlessly and have this Kaveri just increase endlessly. There is a tribunal cap, and then there's an ecologically fragile habitat cap on new sources.
So you mentioned, trying to develop other sources to build a more resilient system. And one of the things that you mentioned in some of your papers is wastewater treatment and potentially reuse. You indicated that in one of your papers that by 2030, you still project that maybe 20% of the wastewater would not be treated. And maybe you can describe a little bit about what are the barriers to enhance water treatment and then potentially to use that as a water source also. So people talk about one water or circular management of water. So I think that's a nice idea. But you're also very cognizant of the energy implications of all of these things. So that's important to consider these days. We can't just say do this and do that and just silo on the water side and forget about energy.
I agree. So in Bangalore's case, there's an energy implication to treatment and reuse, but remember that we're sitting on the top of a mountain, and so all of that is relative to pumping the water up 1,000 meters. So there's that's where the energy trade-off is. I would say in terms of barriers, firstly barriers to treatment, right? If you'd say Bangalore is one of the richest cities in India, we say India's Silicon Valley, it certainly has a lot of billionaires. It doesn't cost that much to build sewage treatment plant for 12 million people. A sewerage, the sewerage network costs money, but sewage treatment itself isn't that expensive. But nonetheless, it's well within the ability of the population to invest in it. And so the question is, why do relatively rich cities still not have sewage treatment? And I think there's kind of two answers to this. One is an awareness answer, which is that people don't necessarily understand the implications that if you're not treating your wastewater, it's actually impacting your own drinking water source. It's rendering certain water bodies that could have been a backstop drinking water source from being used because now they're just too polluted. So one problem is you're shooting yourself in the foot because you're actively destroying your backup water sources. But the other problem is kind of more of a policy incentive kind of an argument, which is that in most cities in India, the water utility gets paid for how much water they deliver, but they don't get paid much more if they actually fully collect and treat all the sewage. And even though you have a water supply and sewerage board, for most part, the sewerage side of that equation is a stick, and the water supply is a carrot. So if you set up your systems in this way, which means that you get more money as you keep expanding your pipe network, which is why even though the city is going crazy, the water supply and sewerage board will keep extending its pipe network to the peri-urban areas because it's more income and it's more money. But on the sewerage side, they're not going to get a whole bunch of extra money to put those sewerage lines. So the only reason they do sewerage is because you get taken to court by, in India, what's called the National Green Tribunal, where the National Green Tribunal comes and says, hey, you're supposed to set up the sewerage system. Here you are allowing all this raw sewage to go into lakes. And so now we're going to fine you if you don't do it. So only till it reaches that point that it gets so bad that they start getting fined, and then they start making investments. And this is perfectly rational behavior for water utilities. So in my opinion, apart from the awareness and people's willingness to pay, the second piece of it is you have to fix some of these policy incentives for water utilities as well to make sure that they actually get paid a separate line on their on the bill volumetrically based on if that ward is completely covered by sewerage and a sewage treatment plant. And then I think so that I think that's one traditional way of thinking about how circularity could be induced. And then I think if you wanted to be more futuristic, I think the direction in which Europe is going, I don't think India is ready for that, is about thinking about wastewater treatment plants as being resource recovery plants. And once kind of your phosphorus prices go up high enough, and so on, which is what's happened in Europe, because India still imports a lot of its phosphorus from Africa, for example, which is cadmium laced and so on. But that's banned in China and Europe and so on. So there, the cost of phosphorus has gone up, and now you're starting to see the incentives for circularity change. So I would say there's sort of a governance side of it, and then there's a market side. And the market side is only going to come in once the right regulations come in, and people start seeing phosphorus as a valuable commodity that can be recovered from sewage. And then suddenly everybody wants to build, even though nobody wants to pay for sewage, people want to value the phosphorus. And so now there's an incentive again to set up sewage treatment. So that's futuristic for India.
Right. So that's fascinating. I mean, you really need to be proactive, because in a short time, discharging sewage to your reservoirs and stuff like that can destroy, and remediating that is a career, so it's very quick to nuke it, but it's a very time intensive and labor intensive then to remediate it. So being a bit more proactive, but that's more easily said than done. So you're really getting at the guts of those issues. And when you say resource recovery, I was laughing because you mentioned, you get your phosphorus from Africa and it's cadmium laden. And my daughter's been telling me the chocolate that I eat has cadmium in it and I should stop eating it, So there are a lot of different things, and that's what's challenging these days. So many things to consider when we try to move forward. So if we broaden the discussion then from Bangalore out to southern India, peninsular India, which is geologically a lot like sub-Saharan Africa, there are some solutions being proposed. People talk about managed aquifer recharge. There are different ways of monitoring the impact of some of these policies. And sometimes it's difficult to figure out what the impact of something is, because there are so many other things going on. Climate is varying, weather is varying, and, other things. And so we use satellite data, gray satellite data, to look at what's happening to the total water storage, but then going down into more details, what's happening with the groundwater levels, what's happening with the farmers, and trying to disaggregate or understand all of these different things is very complicated. Maybe you can describe that. And I know you were commenting recently on, some people wrote about a paradigm shift with the policies and stuff like that, but your on the ground analysis, had a different picture. So maybe you can describe that, Veena.
Yeah, let me talk about two separate things here. One is about the data itself, and the other is kind of how we think about monitoring, evaluation, and learning in the sector. So in terms of data, I think one thing that we, especially people who come from modeling background, we tend to do is we kind of tend to take the data as sacrosanct, right? This is the data, we measured it, it must be true. And we rarely have a mindset of questioning data, saying, is this data even making sense? And so we say, hey, Grace is showing a signal that's going up, or hey, I looked at the monitoring well data and it shows that groundwater levels are stable. And that's the paper that you're referring to, which is the groundwater recovery paradox paper, which was basically showing that groundwater levels were going up in South India. And what we realized is, of course, Grace is very, very coarse. I mean, there's probably a few blocks, all of South India is probably a few grid cells. But even in the groundwater recovery paradox paper, where we were referring to the increases which were coming from looking at long-term monitoring well data. Now, of course, you would say, well, how can that possibly be wrong? It's long-term monitoring well data. I mean, if it's going up, it's going up. And what we discovered was that firstly, the reason we started getting curious is we were like, hey, if the water levels are going up, why are farmers still so miserable? And this is through field work, right? You're talking to farmers, their well is at 1,000 feet, their bore well failure rates are like 80, 90%. And so why is that happening if the monitoring well data in the same locations, right, are showing very, very shallow water levels. So the first thing you realize is that hard rock aquifers are extremely heterogeneous and they are extremely localized. So that means if you have a monitoring well every 100 square kilometers, but sometimes you'll find two wells in the same field which have a water level which could differ by 200 meters. 200 meters, not 2 meters, 200 meters. And this is two wells which are within 10 meters of each other. So the question then is that if there's this kind of heterogeneity, firstly, is it even meaningful to talk about the results from a monitoring well network, which is a well per 100 square kilometers? And the second thing we realized is we said, well, why is that monitoring well network so shallow? Because the government would keep telling us, but we put in new monitoring wells, it's a much higher density, so on and so forth. And what we started realizing is that the problem is that a lot of these wells were continuously getting dry. So the government would put in monitoring wells, they would last a few years and then they would go dry and new wells would come in. And so very few wells were actually surviving to create a long-term trend. But the ones that did were representing hyperlocal perched conditions. And so we had a survivor bias problem in the data when you look at long-term monitoring data, which looks then incredibly stable. But those are so hyper local, it would be the equivalent of keeping a cylinder of glass out in the rain. It empties and fills, and you think, oh, it's got water in it. But it's not connected to anything else. It doesn't have any meaningful interpretation in terms of a regional water table. And so that's kind of where we started questioning the data, and we wrote that paper on the survivor bias. But I would say much later, and now kind of thinking about what we're doing at Well Labs, the larger question we are asking was the question that you said, something that you said before when you posed the question, which is there are so many confounding variables. There is rainfall varies, groundwater conditions vary, the water moves up and down. So you're going to see the same intervention upstream and downstream is going to have different impacts because just of the positionality in the watershed. And so what we realized is that we don't have a good monitoring and evaluation toolkit for the sector. So, the way in the social, in the development sector, randomized control trials became a big thing in the early 2000s, culminating with the Nobel Prize a couple of years ago for SDU Flow and Abhijit Banerjee. We don't have the equivalent of that in the water sector, and the same tools don't exactly work because you can't randomly assign watersheds to a program because then rainfall is confounding, right? And so you're going to have, or one is upstream and one's downstream, and if you don't understand subsurface flows, you're still going to get it wrong. And so what we've started doing is trying to think about how do we develop controls so that if we really want to know what made a difference, what's kind of the set of toolkits that we do so that everything doesn't have to be a PhD science project. So is there any way to simplify and use the best state of the science to arrive at heuristics so we can help the whole sector learn faster than doing everything de novo as a new science project, which takes 5 years.
Well, I think it's great. And, anytime I'm looking at data, you kind of like to talk to people who have boots on the ground and do a reality check with what you're looking at, because all is not what it seems, And so I think that's really insightful. And, we always tout, long-term records, that's the gold standard for hydrology, but the process of just isolating those long-term records, we're biasing the data. So that's extremely interesting, and we do it without thinking. And so I think you highlighted an important issue that we do all the time robotically. And so when you talk to these farmers, then you mentioned when we spoke previously that a lot of these farmers, some farmers have shallow wells, and then some have very deep wells. And that has a big energy implications. But what are they getting when they drill very deep in these basement aquifers that have such low storage? And what are the energy implications? And what would you suggest for some of those farmers?
That's a fantastic question, Bridget. Firstly, the most important thing is the farmer doesn't see the energy implications because many states in Peninsular India have electricity is free. So it's the taxpayer that's is picking up the bill. And so the farmer doesn't see the energy implications of pumping from 1,000 feet. And a lot of these bore wells are between 600 and 1,200 feet. So they're very, very deep bore wells. They're very low yielding bore wells. They don't yield a lot of water because they are fracture fed by a few fractures here and there. A lot of it is just storage in the column itself. It drips and then fills the column, then you pump it up for the day and so on. But it also raises the question of, if we actually start looking at it, if we went beyond the political feasibility of of charging for electricity, which doesn't exist in India right now. No politician is going to ever say that in any foreseeable future, until the demographics of the country completely change and farmers stop being greater than 50% of the voting population. Right now, they're still a very comfortable majority of the voting population, and the motivated voting population is still farmers. So until that changes, you're not going to see political will changing. Now, if you say that we can't do anything about free electricity, that's here to say. Then the question is, what else can you do? And you talked about managed aquifer recharge before. That's, of course, what the bulk of the effort is on, let's say, can we expand the pie, because we can't do anything about what farmers are consuming. So can we just improve recharge? And there are limits to it. There's many parts of Peninsula India which is saturated, because you've invested so much in managed aquifer recharge over 20 years. There's nothing else to recharge. I mean, it's already zero runoff now. So then the question is, what can we do? And here's kind of where the solution space starts becoming really interesting and really creative. There's sort of 2 or 3 interesting spaces where you're beginning to see solutions. One is in the solar irrigation space, kind of basically saying, can you solarize pumps? And more importantly, can you offer feed-in tariffs that are very attractive? So that means the farmer becomes primarily an electricity seller and less of an irrigator. And that incentivizes the farmer to actually only grow highly productive crops, use it efficiently, and then sell the electricity back to the grid. So there's a big push towards pump solarization. The second set of very interesting solutions is around groundwater collectivization. There's a few organizations which have tried to say whether, basically create one way to think about it is to create a grid within the village, so that it connects up all of the bore wells within the village and allows the bore well owning farmers to sell their water to others through that grid within the village. So it's a groundwater collectivization solution, where now the farmer has the incentive, the bore well owning farmer has the incentive to say that I'm going to pump this water and put it into the grid. And now that I know I can get a price for it, I don't have to use it all up myself. And the rain-fed farmers, on the other hand, know that drilling a bore well in a hard rock aquifer to 1,000 feet is so expensive. That's one of the things that drives a lot of farmer suicides. But if you know you can get a little bit of water from your neighbor because you've set up this now village water grid and these collectivization agreements, then you're less likely to say, I'm going to go and put my own bore well in, because you know that that's a pretty risky financial proposition. So there's an organization called Vasan, a nonprofit that's done a lot of work with interesting types of rules and institutions around collective sharing. I think the third solution, which I haven't seen anywhere, it's something that's more of a thought experiment that we have at Well Labs, is, there's very little storage between 200 feet and 800 feet, or between 100 feet and 800 feet. There's almost nothing. And so the carbon cost and the cost to the taxpayer of bringing up the water from 800 to 100 feet is massive, right? It's less carbon incentive, and it's straight money from the taxpayer's pocket. If you're able to set a max on the pumping in the village, and you're able to tell the village exactly what you're pumping today, which is the rainfall is going all the way to 800 feet, and you're pumping it right back up, because there's no extra storage. So you're not like depleting anything of any significance. It's coming out to 3 mm probably of any depletion. So that if you're not depleting storage, you're essentially just using rainfall. And if all you're doing is using rainfall, why can't you use it from 200 feet instead of using it from 800 feet? And so if there was a way to give a financial incentive to the local Gram Panchayat, what we call in India Gram Panchayat, which is the village councils, and tell them, If you bring your water table up to 200 feet, in whatever way, we'll literally give you the difference of all that electricity cost that we are spending from the taxpayer money and see if that would make a difference. That would amount to, we've done calculations on this. It's a substantial amount of money for a village. If that amount that's being spent on futile electricity pumping, which is allowing the rainwater to go through those empty cracks to 1,000 feet and pumping them back. I haven't seen this as a solution. It's something that we are still doing calculations on and as a thought experiment. But I think in a hard rock situation like Peninsula India, there might be a very creative set of solutions here. But these are sort of three buckets where I've seen people try something innovative. And like I said, once you realize that the political will and just taxing people and making them pay isn't going to happen anytime soon, we have to start getting creative.
Right. Fascinating. I mean, what you're talking about, when they drill to 1,000 feet and all they're getting is a little bit of storage, which because most of the weathered aquifer is in the top 100 feet. So that's where most of the aquifer is. And so, but then you've got all the energy implications from pumping from that great depth. So I was talking to Joe Ayotte from the US Geological Survey the other day about arsenic issues in the US. But he has developed a patent, and he's in hard rock aquifer system in the Northeast US. He has developed a patent for a well system. So it has it's almost like a dug well system at the top with about 2-3 meter diameter, and so it has larger storage, and then a small well in the center, and so he can store the extra rainwater during a wet period, and then that provides him some buffer, and then you're not drilling deep. You're getting that storage from a dug well type of system, and he's patented that, so that might be something to consider. So, I mean, there's, you also raise a number of important points, solarizing pumps. So Grundfos in Denmark works a lot with Indian groups and providing solar pumps. They are concerned that, that might result in overexploitation of groundwater because of the essentially free electricity after you have the capital to install that solar pumps. But they already
but
have
that's different because there is a feed-in tariff, right? When India is doing it, they're saying that you can sell the electricity back to the grid. So that would be true if all you could do is use the water, then you're increasing the hours of energy available. But if you can buy the electricity back and that you offer them a good enough tariff, then that's where you start seeing the switch where people will say we're essentially electricity farmers, not only agriculturists.
Right. And I noticed in one of your recent, when I was listening some of the material you had online for World Water Day, and reading some of the stuff you mentioned, and the World Bank had this mantra many years ago: too much, too little, and too polluted. So a lot of people focus on water scarcity, and it was nice that you started off saying we're not day zero, that's not the issue. But it's easy for people to talk about scarcity and doom and gloom, but it's really managing these extremes, because you have strong monsoons, so a lot of times you have too much water, and then during drought, you're very little water. So managing these extremes is a big issue. And so a lot of people talk about managed aquifer recharge, get it into the aquifer, but as you say, many of them are already pretty full. But that study that you did looking at the chemistry and the isotopes and all of the data, how far was that managed aquifer recharge tank system recharging the aquifer, and what were other sources of recharge, which could be unlined canals and leaking pipes and things like that, So it's very easy for us to say, oh, we have this new managed aquifer recharge system, and now we're attributing all of the increase in recharge. It could be a wet weather period, that could be, but we're going to attribute all of it to our policy things, say, oh, it's doing great. And we see the same thing in Arizona. They have underground storage facilities, spreading basins, but then also they switch from groundwater to surface water. So a lot of the recharge is incidental recharge from flood irrigation with surface water. So trying to attribute and trying to understand what the impacts of your policies are, I think is very important. And I think you did that very nicely with that paper where you did that very detailed analysis of the fate of that managed aquifer recharge systems.
Absolutely. That was led by Dan Lafford's group, the paper you're talking about at British Geological Survey. Just to say that it was primarily them with us playing a supporting role. But absolutely, I think that we tend to kind of overemphasize, how important these lakes and tanks are, forgetting that that's like 2% of the area, and it's 2% of the area with essentially a lot of siltation, a silted up water body. It can't possibly do that much compared to what the other 98% can do. And then sometimes we forget that because it becomes easy to just draw circles around lakes and say, oh, that's the recharge zone, and not worry about what are we doing with permeable parking lots, what are we doing with rainwater harvesting from rooftops, all of that, those other distributed forms of recharge.
Right. And I think that maybe refers also to like the sponge city concept that the Chinese put forward, or permeable pavement, as you mentioned, and stuff like that. So I think, we've been talking about a lot of different things, but one thing that I enjoyed talking with you recently, and I hadn't been thinking about, is, going back in time and seeing how we have evolved over the past 30 years. And then we're very confident in our projections, because we have nothing to constrain them. But maybe you can describe a little bit. You are much more in tune with what has happened and how we have evolved over the past several decades, and what that means for how well we can possibly project into the future what might happen.
Absolutely. I mean, I think one of the one of the thought experiments that I like to do is kind of say, when you're looking at any system, would I have been able to predict how it turned out if I was in 1980 with the sets of tools, even if I had the set of tools I had today? And most of the time, the answer is you could not have imagined how the water system would have evolved, because water systems co-evolve with society. And often, one of the reasons, or the impetus for the emergence of social hydrology as a field was this realization that even if you've understood a catchment, your ability to predict the future in the Anthropocene, when humans are kind of modifying and co-evolving with these catchments, is very limited. And unless we kind of broaden our understanding of the system to not just take the past as it is, but interrogate why human society evolved in the way it was, what are the signatures and patterns associated with that co-evolution, only then are you going to be able to get better at what we call building a better crystal ball to look into the future. And I think that's kind of what got me motivated with social hydrology. And then the second piece of it is, often because we don't do that, we make the same, and we don't factor in how humans are going to adapt to any changes that you bring in, whether it's bringing in a dam and everybody switching to water intensive crops, or bringing in drip irrigation and everybody expanding their area under irrigation. Any one of those human responses to stuff that we do, where we assume that we're going to do this and humans are going to behave in exactly the way they were doing before you did this. And no, they evolve and they respond to whatever change you've brought in. And we've now seen these happen enough times around the world that we can learn from them. And so essentially, the field of social hydrology basically said, you can't predict, but you can get better at it if you see how other similar systems have co-evolved. And you start characterizing those interlinkages between human water systems. And so I think we've started doing a lot better with the evolution of the field of social hydrology.
And I think some of my favorite books are those written by behavioral economists, because we have a very simplistic view about how people behave, but really it can be counterintuitive. And as you mentioned, things like, increase irrigation efficiency, you expand irrigated area, these Jevons paradox, or you provide a reservoir and then they increase water use. So it's very important. And that's why I think the strength of your work then comes from your background in social hydrology and linking that and understanding that. And I always, whenever, we look at systems, we always try to see how it has evolved in the past, if you want to try to predict in the future. So I think that's history, understanding that is very important. So we've talked about a lot of different things, Veena, and Bangalore is a nice field lab for you, with the urbanization, rural urban issues, hard rock aquifers and surface water, how you manage both of those, and then decision makers, policies, incentives, carrot versus stick, and all of that sort of thing. And I'm really impressed with the well labs. I mean, that's a fairly large organization. You've got about 40 people working with you in that. And you mentioned also that Bangalore, with the high-tech industry, a lot of very wealthy people, and so hopefully that they're investing back into the water supplies. And I saw that when I worked with people in China, in Shenzhen and stuff, they were investing back to improve the conditions there, and industry was providing funds. So I hope that's happening for you also.
That's absolutely a very large portion of our funds are domestic funders. With the exception of when we do international collaborative research, but apart from that, it's really the high-tech industry and the high net worth individuals that have made their money in tech that are really driving a lot of the kind of creative work that we are able to do.
And lastly, then I would ask, are you optimistic about the future for water in southern India or, broader scale?
I mean, I tend to be optimistic because otherwise I wouldn't be able to get up and go every morning. But I think that I'm also optimistic, or I've become optimistic because I've moved my role from being an observer to a transformer, if you want to call it that. So, when we were observing, we had what we call living labs. By the way, it's well labs, and the labs really is because we see the landscapes in which we work as what we call transformation labs, places that we study with the intention of transformation. And I think that gives me hope because you feel like at least I'm not just watching the ship sink. I'm kind of trying to do something. Sometimes we get cynical and say, are we just, rearranging the deck chairs in the Titanic and doing that really well? But there are other times where I feel like, no, this is meaningful. And I think we moved the needle there. So yeah, I would say they're better and worse days, but overall I'm optimistic.
And I like what you say with well labs. I mean, oftentimes we want to put one solution and say one size fits all, and essentially one size fits nobody. And so it's important to recognize the differences in different regions and what's going on. So that's wonderful. And like you, I kind of got tired of just writing papers and nobody reading them and stuff like that. So I branched into doing these podcasts and enjoying learning and promoting people's work and getting that out into more people to listen to it. So thank you so much, Veena. I wish you all the best with your new adventure, and I'm sure you will be extremely successful. So thanks for your time today.
Thank you very much, Bridget. It's a real honor and it was a pleasure chatting.